You've seen them, right? These absolutely colossal metal giants, just gliding across the ocean like it's nothing. But have you ever really, truly stopped to think about how something that massive doesn't just, sink straight to the bottom?
I mean, it just feels like it breaks the laws of physics. We all know what happens when you drop a chunk of steel in water. It's gone, sinks instantly. And yet, a giant container ship, made from the very same material and weighing hundreds of thousands of tons, just sits there, floating. So what's going on here? What's the secret?
And there it is, the paradox, laid out plain and simple. Same stuff, completely different results. This tells us the secret isn't in what it's made of, but in the how. How it's shaped and the incredible physics that this shape puts to work.
To crack this puzzle, we actually have to take a trip back in time, like over 2,000 years back. We're going to meet a brilliant mind who figured out there's this secret upward force at work anytime something is in a fluid, like the water these ships are sailing on.
That force? It's called buoyancy, and you can think of it as the water itself fighting back. Seriously, imagine the water pushing up on anything that tries to push it down. It's this invisible but incredibly powerful lift that's constantly working against gravity.
The way Archimedes figured this out is basically a simple three-step dance. Step 1, the ship goes into the water. Step 2, it has to shove a whole bunch of water out of the way, right? We call that displacing the water. Then, step 3, and this is the absolute key to everything, the water pushes back up with a force that is exactly equal to the weight of all that water that just got moved.
So what this all means is that you have this epic tug of war going on. Gravity is pulling the massive weight of the ship down. At the same time, buoyancy is pushing the ship up. As long as that upward push from the water is the same as, or even stronger than, the downward pull from the ship's weight, it floats. That's the golden rule right there.
Okay, so the buoyant force has to match the ship's weight. That makes sense. But hang on a minute. How on earth can a ship made of super dense steel possibly push enough water out of the way to create a force that strong?
Exactly. That's the big question, isn't it? We know steel is about 8 times denser than water, so if it were a solid block, there's no way it could displace enough water to equal its own weight. It just can't. And this, my friends, is where the true genius of engineering comes into play.
Okay, here it is, the big secret. A ship isn't a solid block of steel. Not even close. It's really just a cleverly shaped steel shell. And what's on the inside of that shell? Air. Tons and tons of it. A ship is, for all intents and purposes, a giant, carefully shaped bubble of air that's just wrapped in a bit of steel.
And this is where we have to talk about a concept called average density. So you take the total weight of the ship, the steel, the engines, all the cargo, everything, and you divide it by its total volume, and that includes all that empty space full of air. When you do that math, the ship as a whole system is actually less dense than the water it's sitting in. That's the trick. That's the whole game.
All right, so we've cracked the floating part. Check. But that's only half the battle, isn't it? How do you keep an object the size of a skyscraper from just tipping over when the waves get rough? Well, this all comes down to a really delicate balancing act between two crucial points. The first is the center of gravity. We'll call it G. And that's the spot where all the ship's weight is basically concentrated, pulling it down. The second is the center of buoyancy, B, which is the center point of the part of the hull that's underwater, where that buoyant force is pushing up.
Now picture this. A ship is out at sea, and it starts to roll in the waves. As it rolls, the shape of the underwater part of the hull changes, and that makes the center of buoyancy shift around. To figure out what's going to happen next, engineers use this super important calculated point called the metacenter, or M. Put simply, where M is located tells you if the ship is going to roll right back up or if it's going to keep on rolling.
And here we have the one simple rule that keeps sailors safe. As long as that calculated point, the metacenter, M, stays above the ship's center of gravity, G, the forces will actually create a correcting lever that pulls the ship back upright. But if G ever gets higher than M, well, those same forces work to flip the ship over. It's a simple rule, but it has life or death consequences. But, of course, things can still go wrong. Understanding why ships float so well also gives us a really clear picture of why, tragically, they sometimes sink. And it always comes down to these fundamental principles being broken.
I mean, just look at the common causes. Taking on water from a hole, well, that messes up your average density. Overloading with too much cargo, same thing. You're making the whole system too heavy.
Cargo shifting around in a storm. Now you're messing with the center of gravity, destroying your stability. See? It all ties back to the rules we just learned.
And the most famous example of all, of course, is the Titanic. The iceberg didn't just dent the ship, it tore holes in it. Water rushed in, replacing all that precious air that was keeping the ship afloat. The ship's average density started climbing, higher and higher, until it was finally heavier than the water it was displacing, and at that moment the outcome was sealed. Gravity won that final tragic tug of war.
Which brings us right back to today. Our ships are the biggest and most advanced in human history, but they are still governed by the exact same unbreakable laws of buoyancy, density, and stability. And physics has shown us time and time again, when you break those rules, nothing is truly unsinkable. So the real question is, how well have we actually learned the lessons from all those ships that now rest on the ocean floor?